At the center of our galaxy, there exists a region so mysterious and extreme that it has long been inaccessible to science. Sagittarius A is not just a point in space, it is the epicenter of a cosmic enigma. It is an object so dense and compact that not even light can escape from within it. Although we cannot see it directly, its presence is revealed by the frantic behavior of the stars and gas surrounding it. How do we know that a supermassive black hole is hidden there? Why does its influence extend across tens of thousands of light years? The answers to these questions take us to the limits of our understanding of gravity, time, and matter. Unlike black holes that devour everything in their path in bursts of energy, Sagittarius A seems to rest at the center of the Milky Way like a sleeping titan, barely emitting signals to the rest of the universe. However, its apparent tranquility is deceptive. Its gravity is so intense that it can fling stars at incredible speeds and warp the space-time around it. What makes this giant remain silent while other black holes shine violently? What secrets does it hold in its surroundings, where conditions are so extreme that they defy any attempt at direct exploration? Exploring Sagittarius A is akin to peering into the deepest abyss of the known universe. Its study not only reveals the inner workings of our galaxy, but also tests the most advanced theories of physics. Each new discovery about this dark heart brings us a little closer to understanding our place in the cosmos and the invisible forces that govern the lives of stars. Today, we embark on a journey to the galactic center to discover why Sagittarius A is much more than an astronomical curiosity. It is the key to understanding the history, present, and future of the Milky Way. What exactly is Sagittarius A, and why does it fascinate astronomers so much? At the heart of the Milky Way, about 27,000 light-years away from us, lies an object that defies human understanding, Sagittarius A. Its name may sound mysterious, but it actually comes simply from the direction in which it is located in the sky, in the constellation Sagittarius. And the letter A indicates a particularly compact and energetic radio source. But what makes it so special? It is not a common star, nor a planet, nor a simple cluster of matter. It is an object invisible to the naked eye, but detectable by the intense radiation it emits at different wavelengths. When we talk about Sagittarius A, we are referring to the exact center of our galaxy, the place around which hundreds of billions of stars orbit, including our Sun. It is like the core of a cosmic beehive, where gravitational activity reaches extreme levels. If we were to compare, we could say that Sagittarius A is the gravitational anchor that holds the entire galactic structure together, the epicenter around which the great spiral of the Milky Way rotates. However, unlike a bright lighthouse, its presence is revealed more by its effects on the environment than by its own light. What is Sagittarius A really made of? Observations reveal that it is a compact and extremely massive source, so dense that not even light can escape its pull. This is where the big question arises. Are we facing a black hole? All evidence points in that direction. In fact, Sagittarius A is considered a supermassive black hole with a mass equivalent to more than 4 million times that of the Sun. But despite its colossal mass, its size is surprisingly small in astronomical terms. All that weight is concentrated in a volume smaller than that of Mercury's orbit. What is fascinating about Sagittarius A is that, although we cannot see it directly, its existence is inferred by the movement of the stars and gas around it. It is like trying to identify an invisible dancer on a dance floor by observing how all the others spin and accelerate around it. The stars close to Sagittarius A move at incredible speeds, guided by a gravitational force so intense that it can only be explained by the presence of an extremely compact and massive object. In summary, Sagittarius A is the dark and enigmatic heart of the Milky Way, a cosmic abyss whose influence extends far beyond what we can imagine. What leads scientists to suspect that something extraordinary is hidden at the center of our galaxy? To answer this, we must travel back in time to the 1970s. At that time, technology for observing the universe was advancing rapidly, and astronomers were seeking to understand the heart of the Milky Way, a region obscured by dense clouds of interstellar dust and gas. But how do you look through that cosmic fog? The key lay in radio astronomy, a technique capable of detecting radio waves from regions that visible light cannot penetrate. In 1974, radio astronomers Bruce Ballack and Robert Brown, using the Green Bank telescope in West Virginia, detected an extremely compact and bright source of radio waves right at the center of the galaxy. They named it Sagittarius A star, or Sagittarius A, after the constellation in which it is projected, and the symbol SAS to highlight its peculiar nature. The signal was so intense and concentrated that it suggested the presence of a very small but incredibly massive object. Could it simply be a concentration of stars, or was it something much more exotic? The scientific community was intrigued. If one imagines the galactic center as a bustling city, Sagittarius A would be like a particularly intense and mysterious neon light. Researchers knew they were facing a phenomenon unlike anything observed before. The properties of the radio source, its diminutive size, equivalent to that of the solar system, and its power ruled out almost any conventional explanation. Questions began to multiply. What kind of object is capable of emitting so much energy in such a small area? Are we looking at a star, a cluster of objects, or perhaps one of the theoretical black holes proposed by Einstein's general relativity? From that first discovery, the following years were marked by a scientific race to unravel the true nature of Sagittarius A. Increasingly sensitive telescopes were used, and new techniques were developed to measure the motion of stars near the radio source. Each observation added a piece to the puzzle, bringing astronomers closer to the conclusion that, at the center of the Milky Way, resides a supermassive black hole. Thus, the finding of 1974 not only marked a milestone in astronomy, but also opened a window to the deepest mysteries of the cosmos. The discovery of Sagittarius A was the first step in understanding that the heart of our galaxy beats to the rhythm of a colossal and invisible gravitational force. Today, that bright point of radio waves remains one of the most studied and fascinating objects in the universe, reminding us that sometimes the greatest secrets are hidden right in the center of our own galactic home.
If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey.
What makes the center of our galaxy such a peculiar place? If we could travel to that region, we would find an environment radically different from any other corner of the Milky Way. There, space is filled with dense clouds of gas and dust, so thick that visible light cannot easily pass through them. This environment is so extreme that it acts as a veil, making direct observation of what happens in the galactic heart difficult. The temperature of the gas can reach millions of degrees, and the gravitational forces are so intense that they subject everything that comes close to colossal stress. But what about the objects that inhabit this environment? Besides Sagittarius A, the galactic center hosts a large concentration of stars, many of them grouped in compact clusters. There are young, massive stars forming from the surrounding gas, as well as old stars that have survived for billions of years in this chaos. However, proximity to a supermassive black hole is anything but safe. The orbits of these stars can be extremely elliptical, causing some to dangerously approach the gravitational abyss. In this dynamic scenario, collisions and close encounters between objects are common. Did you know that phenomena such as particle jets and sudden bursts of X-rays are observed in the galactic center? These events occur when gas and dust are captured and accelerated by the gravity of Sagittarius A, releasing enormous amounts of energy in an instant. It's as if the center of the galaxy is constantly on the brink of a cosmic storm, where calm is never permanent and any small disturbance can trigger a spectacle of titanic forces. Have you ever wondered how this environment influences the evolution of the galaxy? The galactic center is not just a stage for astronomical violence. It is also an engine of transformation. Intense radiation, stellar winds, and the gravitational field modify the behavior of gas and dust, regulating star formation and determining the fate of stars that venture too close. Ultimately, the environment of the galactic center is a natural laboratory where the most extreme physical laws are put to the test, providing us with essential clues about the deep workings of the universe. How can we be sure that Sagittarius A is, in fact, a supermassive black hole and not something else? The answer lies in the evidence that science has gathered over decades. One of the most compelling clues is the way stars and gas move around this point in the galactic center. Astronomers have observed that hundreds of stars orbit at dizzying speeds in a tiny region, as if they were trapped on an invisible racetrack. For an object to exert such gravitational control over its surroundings, it must possess a colossal mass concentrated in an extremely small space. There is no known object except a black hole that can meet these requirements. But how massive is Sagittarius A really? It is estimated that its mass is equivalent to more than 4 million times that of the Sun. However, all that mass is confined to such a small region that not even light can escape from it. To put it into perspective, if the Sun were a grain of sand, Sagittarius A would be like a mountain of more than 4 million grains, compressed into a volume smaller than Mercury's orbit. This density defies all everyday logic and forces us to think in terms of the most extreme physics. Why can't we see Sagittarius A directly? The answer lies in the very nature of black holes. These objects do not emit light because their gravity is so intense that it traps even photons. The only thing we can detect is the influence it exerts on the matter and energy around it. When gas and dust fall towards Sagittarius A, they heat up and emit radiation before crossing the so-called event horizon, the boundary that marks the point of no return. It's as if the center of the galaxy is shrouded in a dark veil, but the frantic dance of nearby stars reveals the presence of this invisible monster. And how do we know that it is not simply a cluster of smaller objects, like neutron stars or white dwarfs? The answer lies in the precision of the observations. If all that mass were made up of compact objects accumulated together, the collisions and resulting radiation would have been detected long ago. Furthermore, simulations and physical calculations show that such clusters would be unstable and would quickly collapse into a black hole. Thus, the only explanation that fits the data is the existence of a supermassive black hole, an object whose gravitational force is so overwhelming that it defines the very core of our galaxy. Sagittarius A is not only the dark heart of the Milky Way, but also one of the best direct pieces of evidence that supermassive black holes are real and govern the centers of galaxies. How big and massive is Sagittarius A? Really? This is one of the key questions when we try to size up the hidden heart of our galaxy. The answer defies all human intuition. Sagittarius A has an estimated mass of about 4 million times that of the Sun. Imagine for a moment gathering 4 million suns into a single point. Now, what's truly astonishing is that all that mass is compressed into an incredibly small region when compared to astronomical dimensions. The event horizon, that invisible boundary marking the point of no return for matter and light, has a radius of just over 12 million kilometers. It may sound huge, but in reality, it's about 30 times larger than the Sun. To get a clearer idea, if we replaced the Sun with Sagittarius A, its event horizon would comfortably fit within the orbit of Mercury. Why is such a massive object so compact? This is the essence of what defines a supermassive black hole. The extreme gravity of Sagittarius A is so powerful that not even light can escape once it crosses the event horizon. It's as if the entire mass of a city, a country, or even all of humanity were compressed to fit into a single grain of sand. But here, we're not talking about humans or cities. We're talking about millions of suns compressed into a tiny volume on a galactic scale. The size of the event horizon also helps us understand how Sagittarius A interacts with its environment. Everything that happens beyond this boundary remains hidden forever. However, the gravitational influence of Sagittarius A extends far beyond its horizon. It is capable of controlling the orbits of stars that pass billions of kilometers away. Despite its small physical size, its presence is felt across a vast region of the galactic center. It's like an invisible conductor, orchestrating the movement of everything around it. It's paradoxical. Sagittarius A is both immense and tiny at the same time. Its mass is monstrous, but its size, compared to the galaxy, is minuscule. This contrast is one of the reasons why black holes fascinate scientists so much. They challenge us to rethink concepts of space, matter, and gravity. How can something so small, in terms of volume, have such a colossal impact on the workings of the entire Milky Way? The answer remains one of the great mysteries of the cosmos. What really happens at the invisible boundary of a black hole? At the heart of Sagittarius A, that line is known as the event horizon, a region that has fascinated and puzzled scientists for decades. This is the point of no return, a spherical and invisible boundary that marks the threshold beyond which nothing, not even light, can escape. But why does this happen? The answer lies in the extreme gravitational force that Sagittarius A exerts on everything that gets too close. To understand it better, imagine a colossal waterfall where the water flows faster and faster as it approaches the edge. If something crosses that edge, there's no turning back. The current is so powerful that it drags everything irretrievably downward. Similarly, at the event horizon of Sagittarius A, space-time is so curved by the mass of the black hole that even light gets trapped. It's as if gravity weaves a perfect trap from which no one can escape once that boundary is crossed. Have you ever wondered what would happen if a spaceship ventured too close to Sagittarius A? As it approaches the event horizon, the gravitational effects intensify drastically. To a distant observer, it would seem that the ship slows down and freezes just before crossing the horizon, gradually fading away as its light stretches towards the red. However, for the crew on the ship, the journey would be swift and irreversible. Once they cross the region of no return, there would be no way to communicate with the outside or to return. The event horizon is not a physical surface, but a mathematical boundary. We wouldn't find a wall or an abrupt change upon crossing it, just the certainty that any path from that point inevitably leads toward the center of the black hole. Once inside, all known laws of physics as we understand them cease to apply, and information about what happens is lost to the rest of the universe. This mystery makes the event horizon one of the most intriguing and enigmatic regions of the cosmos, a place where time and space are warped to unimaginable extremes. What makes the so-called S-stars so special, and why is their behavior so fascinating for modern astronomy? At the core of the Milky Way, just a few light years from Sagittarius A, a group of stars performs a dizzying dance around the supermassive black hole. These stars, known as the S-cluster, move at incredible speeds and follow elliptical trajectories that defy any experience we can imagine in our solar environment. Some of them, like the famous S2, complete an orbit in just over 16 years, an astonishingly short time considering that, in comparison, the Sun takes more than 200 million years to orbit the galaxy. How is it possible for these stars to survive so close to such a dangerous region? The key lies in their speed. As an S-star approaches its closest point to Sagittarius A, it can reach speeds exceeding 8,000 kilometers per second. It's as if a plane circled the planet in less than 10 minutes. This extreme speed is necessary to counteract the titanic gravitational force of the black hole and avoid being absorbed. Moreover, its curved and accelerated trajectory is direct evidence of the effect of gravity on space-time, as predicted by the theory of general relativity. What do these movements reveal about Sagittarius A itself? The answer is fundamental. By observing how these stars move, astronomers have been able to accurately calculate the mass and even the size of the invisible object that attracts them. The orbit of the S-stars, especially that of S2, behaves as if they are orbiting a compact mass about 4 million times that of the Sun. There is no other plausible physical explanation. That dark and seemingly empty point at the heart of the galaxy can only be a supermassive black hole. Has any unexpected phenomenon been observed while studying these orbits? Yes, and this is where the story gets even more interesting. When S2 passes close to Sagittarius A, the light it emits undergoes a frequency shift, moving towards the red, due to the intense gravitational field. This phenomenon, known as gravitational redshift, has been measured precisely, spectacularly, confirming Einstein's predictions. The S-stars, with their almost suicidal motion and impossible trajectories, have thus become the best natural laboratories to study the extreme physics that reigns in the galactic center. In summary, thanks to the observation of the orbits of the S-stars, humanity has been able to weigh the invisible heart of our galaxy and confirm, with irrefutable facts, the existence of Sagittarius A as a supermassive black hole. These stars, which defy intuition and everyday physics, are the silent messengers of one of the greatest mysteries of the universe. What do a researcher from Los Angeles and a German scientist have in common? Both challenge the deepest mystery of our galaxy and forever transform the way we understand the center of the Milky Way. Andrea Ghez and Reinhard Genzel, two fundamental names in modern astronomy, embarked on a fascinating race to prove the existence of a supermassive black hole right at the heart of our galaxy. How did they manage to convince the scientific world of something that no one could see directly? The key was in observing the stars closest to the galactic center, stars that orbit at breakneck speeds, like Formula One cars racing around an invisible track. Ghez and Genzel, each leading independent teams in the United States and Germany, perfected observation techniques using infrared telescopes and adaptive optics systems. These advancements allowed them to track the movement of the so-called S-stars for over 2 decades. Their orbits, tightly curved and extremely fast around an invisible point, unambiguously revealed the presence of a compact and colossal mass, a black hole millions of times the mass of the Sun. Could there be another explanation for such extreme movements? The data collected by both teams ruled out any plausible alternative, such as star clusters or concentrated dark matter. Only a supermassive black hole could explain the gravity needed to keep the stars trapped in such tight and fast trajectories. The measurements by Ghez and Genzel were so compelling that, in the year 2020, they received the Nobel Prize in Physics for their discovery. This distinction not only recognized their tenacity, but also the revolutionary impact of their work on all of astrophysics. The legacy of Andrea Ghez and Reinhard Genzel goes far beyond a simple confirmation. Their research opened the door to new tests of general relativity under extreme conditions and transformed the galactic center into a natural laboratory for studying phenomena that challenge our understanding of the universe. Thanks to their efforts, we now know that Sagittarius A is not just an astronomical curiosity, but the dynamic, invisible, and enigmatic heart that defines the fate of the entire Milky Way. What other secrets await us in that dark abyss? The race to discover them has only just begun. If we think about supermassive black holes, what makes Sagittarius A special compared to other giants of the cosmos? Although Sagittarius A is the dark heart of the Milky Way, it is actually not the largest black hole we know of. For example, in the galaxy M87 resides a black hole that surpasses Sagittarius A in mass by over 1,000 times. M87A, as it is called, has an estimated mass of several billion times that of the Sun, while Sagittarius A only concentrates around 4 million solar masses. It's like comparing a marble to a soccer ball. Both are spheres, but their sizes are radically different. And how do these colossi behave? Sagittarius A is surprisingly quiet compared to other active black holes, known as quasars. Some of these black holes consume matter at such an extreme rate that they release jets of energy and light capable of eclipsing their entire host galaxy. Sagittarius A, on the other hand, seems to be in a kind of cosmic fasting state. Although it is capable of devouring material, it does so at a slow pace and emits much less brightness than other supermassive black holes with similar characteristics. This difference in activity largely depends on the amount of material available for feeding in the galactic center. Are there other, quiet, supermassive black holes like Sagittarius A? The answer is yes. Many galactic centers harbor black holes that, due to a lack of gas and dust, remain dormant most of the time. However, it only takes a cloud of gas to awaken these monsters and trigger brief bursts of energy. What's fascinating is that, despite its relative calm, Sagittarius A exerts an impressive gravitational influence, keeping nearby stars in dizzying orbits and shaping the dynamics of the galactic core. Finally, the question arises, is Sagittarius AC a typical example of a supermassive black hole, or is it an exception? In reality, it meets most of the essential characteristics: large mass, location at the center of a galaxy, and the ability to alter its environment. However, its low level of activity makes it a unique object for studying the behavior of black holes in silent mode. Comparing Sagittarius A with other supermassive black holes not only helps us understand their differences, but also to decipher the role these objects play in the evolution of galaxies throughout cosmic history. How is it possible to study such a mysterious and hidden object like Sagittarius A when it is surrounded by dense clouds of dust and gas that block most of the visible light? The answer lies in observing the universe through different eyes, using multiple wavelengths. Just as a doctor needs different tests to understand a patient's condition, astronomers turn to radio astronomy, X-rays, and infrared to reveal the secrets of the heart of our galaxy. Radio astronomy was the first tool that allowed the detection of Sagittarius A. Radio waves, unlike visible light, can pass through interstellar dust without much difficulty. This ability allows us to hear the echoes from the galactic center, as if we had a radar penetrating the fog. Thanks to radio telescopes, scientists captured the intense emission of energy coming from an extremely compact region, which provided the first clue about the existence of an extraordinary object in that location. But why also use X-rays and infrared? X-ray emissions are vital because they reveal the most energetic and violent processes near the black hole. When gas and dust fall towards Sagittarius A, they heat up to millions of degrees and emit X-rays before crossing the event horizon. Observing in X-rays is like watching the fireworks of extreme physics, allowing astronomers to study flares and eruptions that would be invisible in other frequencies. Meanwhile, infrared plays another fundamental role. It allows us to track the orbits of stars that are very close to Sagittarius A, even when they are hidden behind thick curtains of dust. It's as if we had night vision to follow the dance of the stars deep within the galactic core. Each wavelength contributes a unique piece to the puzzle. Together, they provide a much more complete view of what happens in the vicinity of Sagittarius A's. What do these different colors of the universe reveal? On one hand, they show the structure of the accretion disk, the behavior of magnetic fields, and the dynamics of stars and gas clouds in the immediate environment of the black hole. On the other hand, they allow us to understand the variability of Sagittarius A, its episodes of heightened activity, and the periods when it remains calm. Multispectral observation is, therefore, essential to unravel the mysteries of Sagittarius A. Without the combination of radio, X-rays, and infrared, our understanding of the galactic center would be like trying to assemble a puzzle with most of the pieces missing. Thus, science continues to add layers of information, opening new windows to an invisible universe to our eyes, but fascinatingly revealing through technology. What does it take to observe something that, by definition, is invisible? That was the nearly impossible mission undertaken by the Event Horizon Telescope, known as EHT. Why is it called that? Because its main objective is to study the event horizon of black holes, that mysterious boundary where gravity becomes so intense that not even light can escape. But how can a telescope see something that doesn't emit light? The key is to look at the immediate surroundings of the black hole, where matter and energy reach extreme levels before being devoured forever. The EHT is not a traditional telescope. It is not a single massive instrument pointing at the sky from one location. In reality, it is a global network of radio telescopes distributed across different points on the planet, from Antarctica to Hawaii, passing through America and Europe. By synchronizing their observations with precision to fractions of a second, these observatories work together as if they were a single telescope the size of the Earth. This technique, called very long baseline interferometry, allows for such astonishing resolution that, in theory, we could read a newspaper on the surface of the Moon from our planet. Why is such resolution necessary? Because the event horizon of a supermassive black hole, although gigantic in cosmic terms, appears tiny from Earth due to the vast distance that separates us. What is the challenge? Sagittarius A is hidden behind dense clouds of gas and dust that block visible light and most electromagnetic waves. However, radio waves, like those captured by the EHT, can penetrate this galactic veil. By combining the data collected by each station, scientists managed to reconstruct an image of the immediate surroundings of Sagittarius A, capturing the shadow that the black hole casts on the bright disk of material surrounding it. It's like trying to reconstruct the silhouette of a dark object submerged in a lit pool, using only the waves that manage to penetrate the water. But what revelations has the EHT allowed? By obtaining direct images of the environment of a black hole, the EHT offers the possibility to test fundamental theories of physics, such as Einstein's general relativity, under the most extreme conditions that exist in the universe. Additionally, it has allowed for unprecedented precision in measuring the size and shape of the black hole's shadow, essential information for understanding its mass, dynamics, and interaction with the surrounding material. Ultimately, the Event Horizon Telescope has transformed what was once pure speculation into direct observation, opening a new window to the study of the deepest mysteries of the cosmos. This project not only represents a technological milestone, but also an example of international scientific collaboration. More than 300 researchers from different countries have joined their efforts and knowledge to make the unthinkable possible, observing the dark heart of our galaxy. Thus, the EHT reminds us that, even when we seek the invisible, the union of science and human perseverance can lead us to discover the unimaginable. What did it really mean to obtain the first direct image of Sagittarius A in the year 2022? For decades, scientists dreamed of seeing the face of our supermassive black hole, but the task seemed almost impossible. How do you photograph the invisible, that which by definition doesn't even let light escape? This question led humanity to one of the most ambitious experiments in modern astronomy. To achieve this, it was necessary to unite telescopes spread across the planet, creating a virtual observatory the size of the Earth. This network, known as the Event Horizon Telescope, allowed for a resolution so astonishing that it is equivalent to distinguishing an orange on the surface of the Moon from our planet. The result was a historic image, a sort of blurry and bright ring surrounding a dark central region. But what are we really seeing in that image? The luminous ring corresponds to the light emitted by gas and dust swirling at extreme speeds around the black hole, just before crossing the point of no return. The dark area in the center, called the shadow of Sagittarius A, is the silhouette projected by the event horizon, the boundary beyond which nothing can escape. This shadow is not a solid object, but a mark left in space-time by intense gravity. Seeing it, even indirectly, is a powerful confirmation of the general theory of relativity proposed by Einstein over a century ago. Why was the achievement of 2022 so revolutionary? Unlike the previously obtained image of the black hole in galaxy M87, Sagittarius A presents additional challenges. It is much smaller in angular size, and its environment changes rapidly, as if we were trying to photograph a hummingbird in mid-flight. The gas and material surrounding it move so quickly that the captured image is the result of combining thousands of snapshots taken over several hours. Processing this data required extremely advanced algorithms and the international collaboration of hundreds of scientists. Thanks to this global effort, we finally managed to observe the footprint of our own central black hole. Beyond the technological feat, the image of Sagittarius A offers us a unique window into the heart of the Milky Way. It allows us to compare theory and observation, test the limits of physics, and better understand how supermassive black holes work. Moreover, it raises new questions. Why do the shape and brightness of the ring fluctuate? What secrets about matter and extreme gravity will Sagittarius A reveal to us in the future? This image is not just a photograph. It is the starting point for exploring the deepest mysteries of the cosmos and a reminder of how far human curiosity can go when combined with technology and international collaboration. What happens when a colossal amount of gas and dust travels through space, approaching the gravitational abyss of a supermassive black hole? In the case of Sagittarius A, this material does not fall directly in a straight line toward the center, but rather, due to its own movement and the immense gravity of the black hole, it begins to spin and form what astronomers call an accretion disk. This disk acts like a kind of cosmic whirlpool, where matter swirls faster and faster as it approaches the edge of the unknown. But why does this material heat up so much? As the gas and dust particles spin and rub against each other, friction transforms motion into heat, raising the temperature of the disk to millions of degrees. Imagine a skater spinning on ice. The faster they spin, the harder it is to stay in control. Similarly, the gas in the accretion disk spins at dizzying speeds and heats up so much that it emits radiation in different wavelengths, such as X-rays and radio waves. However, in Sagittarius A, the amount of available material is relatively low compared to other active black holes, so the disk is faint and the radiation is weak. Does all the material in the disk end up being devoured by the black hole? The answer is intriguing. Only a small fraction manages to cross the event horizon, that point of no return. The rest may be expelled in the form of winds or jets, or remain orbiting for a long time before succumbing to gravity. This accretion process is chaotic and variable. Sometimes the disk becomes brighter when it receives a surge of fresh gas, and at other times it remains in a state of apparent calm, almost as if the galactic monster is asleep. The existence of the accretion disk not only reveals the veracity of Sagittarius A, but it is also a key clue to understanding the behavior of material in the most extreme environments of the universe. Through the study of accretion, scientists can estimate the mass, rotation, and dynamics of the black hole, as well as observe phenomena like the sudden bursts of energy produced by the fall of matter fragments. Thus, the disk of material surrounding Sagittarius A is not just a spectacle of physics, but a window into the deepest secrets of the galactic center. Why does Sagittarius A seem so quiet compared to other supermassive black holes? It's a question that has puzzled astronomers for decades. While at the center of other galaxies we can find black holes devouring matter like cosmic vacuum cleaners, launching jets of energy and radiation that span thousands of light years, our central black hole remains, in relative terms, calm. What accounts for this apparent calm at the very heart of the Milky Way? The key lies in the amount of material that Sagittarius A has available to feed on. The most active supermassive black holes are surrounded by dense clouds of gas and dust, constantly falling toward the event horizon, releasing enormous amounts of energy in the process. However, Sagittarius A lives in a much sparser environment. It's like having a campfire. If you throw in a lot of firewood, it burns brightly. If it has almost no firewood, it barely gives off heat and light. In the case of Sagittarius A, the firewood, that is gas and dust, is very limited, which is why its brightness is dim and its energy emissions modest. But is it just the lack of material that makes it discreet? Not entirely. In addition to the scarcity of fuel, the way gas approaches the black hole is crucial. In Sagittarius A, Much of the matter that should fall toward the center is expelled before crossing the event horizon, due to instabilities, magnetic fields, and extreme turbulence. It's as if the food were within reach, but the plate kept moving, preventing the black hole from fully feeding. Does this mean that Sagittarius A will always be this quiet? Not necessarily. If at any moment a cloud of gas or a star were to come too close, it could trigger a phase of intense activity, with flashes and energy emissions much more powerful. For now, however, Sagittarius A remains like a sleeping giant. Its presence is felt through the gravity it exerts on everything around it, but its voice, in terms of released energy, is barely a whisper in the vast concert of the cosmos. Thus, our galaxy lives for the moment in relative calm, under the influence of this enigmatic and discrete black hole. What would happen if the heart of our galaxy, usually serene and dark, suddenly emitted a burst of energy? Sagittarius A, although it typically remains calm, is capable of producing sudden bursts of radiation. Why does this happen? The key lies in its unpredictable nature. Sometimes, Sagittarius A suddenly shines, releasing energy across a spectrum that ranges from infrared to X-rays. These bursts can last from minutes to a few hours, and while they may seem like dramatic signals from the galactic center, the reality is that they are mysterious events that still challenge science. What causes these bursts? The most accepted explanation is that small fragments of gas or matter fall toward the black hole and, just before crossing the event horizon, reach dizzying speeds and extreme temperatures. This process releases an immense amount of energy in a short time, as if a spark ignited a bonfire in the midst of darkness. It's a cosmic spectacle. Matter accelerated to speeds close to that of light, spinning frantically before disappearing without a trace. Are these bursts dangerous for Earth or the solar system? Fortunately, the distance between Sagittarius A and us is so vast that its eruptions pose no threat to our planet. However, these phenomena are crucial for astronomers, as they allow for close study of the extreme processes occurring in the vicinity of a supermassive black hole. Each burst is a fleeting window that lets us peek into the inner workings of this galactic titan. Why does Sagittarius A sometimes remain inactive for long periods and then suddenly awaken with a burst? The answer is still up for debate. Some scientists believe there are clouds of gas or fragments of asteroids that, when they get too close, are consumed in sporadic episodes. Others suggest that the magnetic fields around the black hole reconnect and release energy unpredictably, much like solar flares, but on a much larger scale. Thus, the variability and bursts of Sagittarius A not only challenge our understanding, but also remind us of how dynamic and surprising the hidden heart of the Milky Way can be. Can a black hole influence the shape and evolution of an entire galaxy? The answer seems incredible, but in the case of Sagittarius A, the supermassive black hole at the center of the Milky Way, it is crucial to understanding how our galaxy became what it is today. Although at first glance a black hole might seem like a mere cosmic sinkhole, its presence has had a decisive impact on the history of the Milky Way since its early days. To understand this connection, it is necessary to imagine the Milky Way as a constantly growing city. At the center of that city, Sagittarius A acts as a silent authority, capable of regulating the behavior of its inhabitants, which in this case are the stars, gas, and interstellar dust. Current theories suggest that the formation of supermassive black holes and galaxies are closely intertwined. In fact, it is suspected that Sagittarius A began to form almost at the same time as the Milky Way, growing as the galaxy accumulated matter and organized itself into its characteristic spiral structure. But how can such a small object, compared to the galaxy, exert such influence? The key lies in its extreme gravity, capable of affecting the dynamics of the gas and dust that, when condensed, give rise to new generations of stars. It is believed that in its early stages, Sagittarius A may have been much more active, emitting powerful jets of energy and galactic winds, which would have regulated the rate of star formation in the central regions. In a sense, this black hole has been both creator and destroyer, preventing all available gas from turning into stars at once and allowing the Milky Way to evolve in a balanced manner. Moreover, the relationship between the mass of Sagittarius A and the mass of the central bulge of the Milky Way is a fascinating enigma. Is it the black hole that determines the growth of the galaxy, or is it the galaxy that feeds and helps the black hole grow? The answer is still not definitive, but research points to a kind of dancer and music where both evolve together and condition each other. Understanding this delicate balance is key to deciphering not only the origin of the Milky Way, but also that of many other galaxies in the universe. Finally, we cannot forget that Sagittarius A represents a window into the most extreme and ancient processes of the cosmos. Studying its influence on the formation of our galaxy helps us answer one of the deepest questions in astronomy. How do the gigantic structures of the universe arise? Although many mysteries remain to be solved, Sagittarius A is undoubtedly one of the main protagonists in the history of the Milky Way. What happens when an interstellar gas cloud ventures too close to Sagittarius A's? The answer to this question reveals one of the most fascinating phenomena at the heart of our galaxy. Sagittarius A's, the supermassive black hole lurking at the center of the Milky Way, is not alone. Around it orbit gigantic gas clouds, moving like butterflies drawn to a lamp in the night. But what happens when one of these clouds approaches too closely to the gravitational abyss of Sagittarius AP? A notable case is that of the gas cloud known as G2, which in 2014 became the star of a cosmic spectacle. Astronomers observed how G2, a cloud with several times the mass of Earth, dangerously approached the black hole. Many expected to witness a dramatic event, the cloud being torn apart and devoured, producing a burst of energy. However, the outcome was much more intriguing. Instead of being completely destroyed, G2 survived the encounter, though not unscathed. Part of its material was stretched and heated, releasing radiation, while the rest continued its journey through the galactic center. Why wasn't it annihilated? The answer is still a subject of debate, but it suggests that G2 might contain a star within it, which would have allowed it to withstand the deadly embrace of Sagittarius A's. These interactions not only represent astronomical spectacles, but also offer vital clues about the behavior of the black hole and its surroundings. Can the passage of a gas cloud awaken an apparently dormant black hole? In theory, yes. If enough material is captured, the accretion process can accelerate, generating bursts of X-rays and radio waves. It's as if the black hole suddenly received an unexpected feast after centuries of fasting. But so far, Sagittarius A has remained relatively modest, lacking the violent outbursts seen in other, more active galactic centers. Furthermore, studying these encounters allows scientists to test the laws of physics under extreme conditions. The gas approaching the black hole experiences tidal forces so intense that it can be stretched like spaghetti, a phenomenon known as spaghettification. This not only transforms the cloud, but also provides a unique opportunity to observe how matter interacts with the strongest gravity in the universe. Thus, each gas cloud that dares to approach Sagittarius A becomes, unknowingly, a natural experiment that helps unravel the mysteries of the cosmos. Finally, these interactions affect the evolution of the galactic center. Could repeated encounters with gas clouds gradually feed Sagittarius A, influencing its growth over millions of years? Although the amount of material captured each time is small compared to the total mass of the black hole, these processes, repeated over cosmic timescales, can have a cumulative impact. Thus, the ebb and flow of gas clouds around Sagittarius A is not only an impressive phenomenon, but also a key piece in the dynamics and history of our galaxy. What really happens when an object gets too close to Sagittarius A? The answer is that it enters a world where the normal laws of physics seem to fade away. The gravity near this supermassive black hole is so intense that anything approaching its event horizon, from gas and dust to entire stars, experiences extreme forces capable of tearing matter into its most basic components. It's as if space itself is warped, stretching and compressing objects in a phenomenon known as spaghettification. Can you imagine a place where the difference in gravity between your feet and your head would be so vast that your body would be stretched to the limit? Not only objects suffer these forces. Light, which normally travels in a straight line, is also caught in the gravitational whims of Sagittarius A. As it approaches the black hole, light rays curve so much that, in some cases, they can orbit the black hole several times before escaping, or never escape at all. This effect, known as gravitational lensing, even allows us to see distorted images of objects that are behind the black hole. Thus, the space-time around Sagittarius A becomes a true cosmic mirror, challenging our understanding of reality. But how does all this affect time? Near Sagittarius A, time does not progress the same for everyone. For a distant observer, a clock approaching the black hole would tick slower and slower, almost stopping at the edge of the event horizon. From the perspective of someone falling in, time would continue normally, but they would never be able to send a final message to the outside. This extreme time dilation is not just a theoretical curiosity. It has been confirmed by precise observations of stars orbiting near Sagittarius A, showing that Einstein's general theory of relativity holds true in one of the most extreme environments in the universe. The gravitational influence of Sagittarius A doesn't stop there. The very structure of the Milky Way depends, in part, on the presence of this invisible titan. Its gravity dominates the galactic center, controlling the dance of millions of stars, clouds of gas, and even mysterious clusters of dark matter. The orbits of nearby stars become elliptical and fast, as if they are trapped in a cosmic carousel that defies all logic. Ultimately, Sagittarius A is the silent sculptor of the heart of our galaxy, shaping space and time around it, with a force that defies human imagination. What happens to information when something falls into a black hole? This is one of the deepest and most perplexing questions in modern physics, and it lies at the heart of the so-called information paradox. Think of a book, a star, or even a spaceship. All contain information, whether in the form of mass, energy, chemical composition, or particle configuration. If these objects cross the event horizon of a black hole, like Sagittarius A, is that information lost forever? The classical theory of black holes, based on general relativity, suggests that yes. Nothing, not even light or the most basic data, escapes once it has crossed that invisible boundary. However, quantum mechanics tells us something very different. According to its principles, information cannot disappear from the universe, not even under the most extreme conditions. This contradiction has sparked intense debate among physicists for decades. Can the universe break its own rules? Or is there some still unknown mechanism that allows for the recovery of lost information? Some scientists have compared this paradox to shredding an important document and then trying to reconstruct it from the ashes. Is it possible, or is the destruction absolute? Stephen Hawking was one of the first to point out the gravity of this problem. According to his calculations, black holes emit a faint radiation, known as Hawking radiation, that over time can cause the black hole to disappear. But this radiation seems to be completely random, with no trace of the information that fell inside. Thus arises the dilemma. If the black hole evaporates and the information is not recovered, it would violate the fundamental principle of information conservation in quantum physics. This unsettling possibility has led to the formulation of multiple hypotheses, from the existence of holographic copies at the event horizon to quantum tunnels or parallel universes. Today, the information paradox remains unresolved. Could the key lie in an even deeper theory that unites the principles of relativity and quantum mechanics? Or perhaps our understanding of information itself needs to change? The fascinating aspect of this mystery is that, in trying to decipher what happens at the heart of a black hole, scientists might uncover new fundamental laws of the universe. The information paradox not only challenges our understanding of Sagittarius A, but also tests the very limits of reality itself. Is it possible that the dark heart of the Milky Way also pulses, in a way, sending waves through the very fabric of the universe? Gravitational waves are those vibrations of space-time predicted by Albert Einstein over a century ago, and only recently have we managed to detect them. But what connection does Sagittarius A have with this fascinating phenomenon? Although most of the gravitational waves detected so far come from mergers of smaller black holes, the role of a colossus like Sagittarius A in this context is one of the most intriguing questions in modern astrophysics. To understand this, let's think of space-time as the surface of a calm lake. When two extremely massive objects, like black holes, orbit around each other and eventually merge, they produce waves that propagate across that lake, traveling through the cosmos. Sagittarius A, with its mass millions of times that of the Sun, is like a gigantic stone in the center of that lake. If another supermassive black hole ever got close enough to dance a deadly spiral with Sagittarius A, the collision would produce a gravitational wave so intense that it could be detected even billions of light years away. But could Sagittarius A generate gravitational waves on its own, without merging with another black hole? In theory, gravitational waves can also arise when very massive objects, like neutron stars or even clouds of gas, pass nearby and are violently accelerated by the extreme gravitational field. However, these waves would be much weaker and harder to detect with current technology. That's why astronomers are keeping an eye on the possibility that, in the future, Sagittarius A might participate in a cosmic collision with another black hole, releasing a signal impossible to ignore. And what importance would it have to detect gravitational waves coming from the center of the galaxy? It would not only confirm the presence and behavior of Sagittarius A as a supermassive black hole, but it would also open a unique window to study the laws of physics under extreme conditions. It would be like listening to the deepest heartbeat of our galaxy, revealing secrets about the evolution of galaxies, dark matter, and the very nature of space-time. Currently, gravitational wave observatories like LIGO and Virgo are fine-tuning their instruments for that great moment. We don't know when it will happen, but the universe and Sagittarius A could surprise us at any moment with a symphony of gravity impossible to silence. Could dark matter exist near Sagittarius A? This is one of the most fascinating questions in modern astrophysics. We know that dark matter is a form of matter that does not emit or reflect light, but whose presence is detected through its gravitational effects. In fact, it is estimated that approximately 85% of the matter in the universe is dark matter, although no one has managed to observe it directly. If dark matter permeates galaxies, what happens in the very heart of the Milky Way, where Sagittarius A resides? Scientists have theorized that dark matter could concentrate in large amounts around the galactic center. Some models suggest that, attracted by the intense gravity of Sagittarius A, dark matter would form a kind of invisible halo, much denser in the vicinity of the black hole. To visualize it, imagine Sagittarius A as the core of an onion, surrounded by layers of an invisible substance that affects the behavior of the stars and gas around it, even though we cannot see or touch it. Is there evidence that this is the case? So far, the evidence is indirect but intriguing. The movements of stars near the galactic center do not always perfectly match what we would expect if only visible matter were present. Some deviations could be explained if there is an accumulation of dark matter in that region. Additionally, certain theories propose that dark matter could influence the very evolution of Sagittarius A, regulating the amount of material that the black hole can absorb and affecting the formation of new stars. However, finding clear signals of dark matter in the vicinity of Sagittarius A is like searching for footprints in the snow during a storm. Any trace is easily erased or confused by other extreme phenomena. astronomers resort to computational simulations and observations at different wavelengths to try to unravel this mystery. Could dark matter be interacting with the black hole in ways we do not yet understand? Solving this enigma would not only help us understand the galactic center, but could also provide fundamental clues about the nature of dark matter throughout the universe. The search continues, and each new piece of data brings humanity a little closer to unveiling one of the deepest secrets of the cosmos. How present is Sagittarius A in our daily lives, beyond telescopes and science? While it may seem like an enigma reserved for astrophysicists, the reality is that this mysterious black hole has left its mark on popular culture in surprising ways. From science fiction novels to major film productions, its presence has served as a source of inspiration and as a symbol of the mystery and majesty of the universe. Why does the idea of a dark heart at the center of our galaxy fascinate us so much? Perhaps because Sagittarius A represents that boundary between the known and the unknown, a reminder that the cosmos still holds unfathomable secrets. In cinema, black holes are often the protagonists of stories where time and space twist, and Sagittarius A has been directly mentioned in films like Interstellar, where the extreme effects of gravity and time dilation are explored. Have you ever wondered if it's possible to travel to the galactic center and survive to tell the tale? Screenwriters and directors have used Sagittarius A as the backdrop for epic adventures, where real physics blends with imagination to take us to places where the laws of nature seem to break down. Even in animated series and video games, the name Sagittarius A appears as the final destination of impossible missions or the origin of mysterious forces. Literature is no exception. Science fiction authors have played with the idea of advanced civilizations hiding near the galactic center, or messages coming from the vicinity of Sagittarius A, as if it were a dark beacon to which humanity directs its curiosity and hope. What would happen if we ever managed to send a probe and receive answers from that distant and dangerous region? The central black hole of the Milky Way thus becomes another character, as intriguing as any hero or villain, capable of unleashing stories of survival, discovery, and wonder. Music and visual art have also found inspiration in Sagittarius A. There are albums and songs that bear its name, evoking feelings of emptiness, mystery, and irresistible attraction. For many, Sagittarius A is like a metaphor for humanity's longing to explore the unattainable, a symbol of the vastness that surrounds us and the questions we still do not know how to answer. In the end, this astronomical object, invisible to the human eye, has managed to become a cultural icon, demonstrating that the universe is not only studied, it is also dreamed and imagined. Observing Sagittarius A represents one of the greatest challenges of modern astronomy. Why is it so complicated to study this object at the heart of the Milky Way? To begin with, its location is about 27,000 light-years away, in a densely populated region of stars, gas, and interstellar dust. This layer of gas and dust acts like a curtain that blocks visible light, rendering conventional telescopes useless for directly observing the galactic center. It's like trying to see the center of a city shrouded in fog from hundreds of kilometers away. The details simply get lost along the way. But this is not the only obstacle. Earth's atmosphere introduces additional distortions in astronomical observations. Radio waves, infrared, and X-rays can penetrate part of this cosmic veil, but even so, the signals that reach our instruments are incredibly weak and often contaminated by background noise from other galactic sources. How can we distinguish the faint voice of Sagittarius A amidst the deafening clamor of the galaxy? Astronomers have had to develop sophisticated techniques such as very long baseline interferometry, which involves combining signals from various radio telescopes distributed around the planet, simulating a telescope the size of the Earth. Moreover, there is another fundamental challenge: the variability and apparent smallness of Sagittarius A. Although its mass is enormous, its angular size in the sky is tiny, comparable to trying to read a coin on the surface of the Moon from Earth. Rapid changes in its emission complicate the acquisition of sharp and detailed images. Scientific teams must synchronize observations in very precise time windows, dealing with Earth's movement, atmospheric conditions, and time zone differences between observatories, all to capture the brief breath of energy emitted by the black hole. Finally, interpreting the data is a true puzzle. How can we be sure that what we observe actually comes from Sagittarius A and not from nearby phenomena or instrumental effects? Scientists must compare multiple observations, discard artifacts, and rely on complex theoretical models to reconstruct the most accurate image possible of the black hole's environment. Each advancement made not only requires cutting-edge technology, but also creativity and persistence to overcome the limits imposed by our own planet and the vast universe. Thus, every piece of data obtained about Sagittarius A is a small victory in the struggle to unveil the deepest secrets of the cosmos. How is it possible to study an object that, by definition, does not emit light and is surrounded by extreme conditions? This is where simulations and theoretical models come into play. Scientists cannot get close to Sagittarius A to observe it up close, but they can recreate its behavior using supercomputers. These simulations allow them to test different hypotheses about how matter and energy behave in the vicinity of a supermassive black hole, something that would be impossible to experience in reality. What happens when a gas cloud gets too close? How does the accretion disk rotate under the effects of such intense gravity? Simulations provide us with a virtual laboratory to observe these phenomena in detail. A fascinating example is the modeling of the gas and dust disk surrounding Sagittarius A. Astronomers input the equations of general relativity and fluid physics into their programs, generating images and animations that predict how the material should appear as it approaches the event horizon. In fact, many of the most impressive images of black holes circulating on the internet are not real photographs, but the result of these simulations. Thus, theoretical models help interpret the signals we receive, from flashes in X-rays to variations in infrared light, and to distinguish whether they come from the black hole itself or its immediate surroundings. But can these simulations really tell us what Sagittarius A is like? Although no model is perfect, the comparison between predictions and real observations has allowed us to refine our understanding. For example, different accretion scenarios have been simulated, from orderly material flows to chaotic turbulence, and then compared with the behavior observed in the galactic center. When the data matches what is predicted by a simulation, scientists gain confidence that their theories are on the right track. And when they do not match, the opportunity arises to discover new physics that is not yet understood. Simulations have even allowed us to explore intriguing questions such as, what would happen if Sagittarius A Psi had a much stronger magnetic field, or if it were consuming matter at a different rate? These tools have been essential in understanding why Sagittarius A Psi is relatively quiet compared to other supermassive black holes, and also in predicting how its behavior might change in the future. Ultimately, theoretical models and simulations act as a bridge between theory and observation, bringing us closer to unraveling the mysteries of the dark heart of our galaxy. What does the future hold for the exploration of Sagittarius A? Although we have already achieved impressive feats, such as obtaining the first image of its shadow, humanity has only scratched the surface of what this enigmatic black hole can teach us. Astronomers are designing increasingly sophisticated instruments capable of capturing even finer details and penetrating the dense cloud of dust that obscures the galactic core. For example, improvements are planned for the Event Horizon Telescope, which will allow for real-time observations and higher resolution. Can you imagine being able to see, almost live, how gas and dust swirl frantically before being consumed by the black hole? But technology doesn't stop there. New radio telescopes, like the ambitious SKA project, the largest radio telescope in the world, promise to map the environment of Sagittarius A with unprecedented precision. Thanks to these advancements, scientists hope to unravel mysteries such as the origin of sudden bursts of energy, the exact dynamics of accretion disks, and the possible interaction between Sagittarius A and dark matter. Will it ever be possible to directly detect dark matter, thanks to the effects it produces in the deepest region of the galactic center? Another frontier opens with the detection of gravitational waves. Future space missions, like LISA, will seek to capture the tiny vibrations of space-time generated by extreme events near Sagittarius A. This would allow for the study of the physics of supermassive black holes under conditions impossible to replicate on Earth. Will we literally be able to hear the gravitational echoes of Sagittarius A and better understand the nature of gravity? The future of research on Sagittarius A will also depend on the development of supercomputers and increasingly complex theoretical models. Simulating the chaotic and extreme environment of the galactic center is like trying to recreate a perfect storm on a cosmic scale. Scientists seek to answer fundamental questions. How does Sagittarius A influence the evolution of the Milky Way? Are there other exotic objects still hidden near this black hole? Each advance brings us closer to understanding not only the dark heart of our galaxy, but also the deeper laws that govern the universe. How special is Sagittarius A compared to black holes in other galaxies? By observing the centers of nearby and distant galaxies, astronomers have discovered that nearly all large galaxies harbor a supermassive black hole at their core. However, not all of these black holes behave the same way, nor do they have the same mass or exert the same influence on their surroundings. For example, the black hole at the center of the elliptical galaxy M87 is much more massive than Sagittarius A, with a mass of several billion times that of the Sun, while Sagittarius A's has a figure close to 4 million solar masses. This difference is like comparing a mountain to a hill. Both are impressive, but one dominates the galactic landscape much more. Is the Milky Way an exception or the rule? It turns out that, in many ways, our central black hole is rather modest when compared to the true monsters of the cosmos. In fact, there are active galaxies, called quasars, whose cores are fed by black holes that devour matter at a frenzied pace, emitting colossal amounts of energy that eclipse all the stars in the galaxy combined. Sagittarius A, on the other hand, is relatively calm. Its low activity makes it seem almost asleep compared to its more voracious relatives. This tranquility has allowed life in our galaxy to develop without the constant threat of extreme radiation coming from the center. What does the comparison between Sagittarius A and other black holes tell us about galactic evolution? By analyzing galaxies of different types and sizes, scientists have found an intriguing relationship between the mass of central black holes and the mass of the surrounding galactic bulge. It's as if there exists a kind of cosmic dialogue. The growth of the black hole and the development of the galaxy are connected, influencing each other over billions of years. This correlation suggests that, although Sagittarius A may not be the largest, it has played a fundamental role in the history and shape of our galaxy, just as it does in other systems. Could Sagittarius A merge with another supermassive black hole, as has happened in other galaxies? Collisions and mergers of galaxies are common events in the history of the universe. When this occurs, their central black holes can get close and eventually merge, releasing gravitational waves that travel across the cosmos. Thus, Sagittarius A is not only comparable to black holes in other galaxies, but it could also be the protagonist of one of the most spectacular events in the universe in the distant future. In summary, although our central black hole does not hold the record for size or energy, its existence and behavior offer a privileged window to understand the dark heart that beats at the center of almost all known galaxies. What if I told you that, at the heart of the Milky Way, there exists an invisible titan that dominates the choreography of millions of stars? That titan is Sagittarius A, the supermassive black hole that, although we cannot see it, exerts a vital gravitational influence on the dynamics of our entire galaxy. But how can an object that emits no light direct the movement of structures as vast as the spiral arms of the Milky Way? To understand its role, imagine a gigantic dance floor where billions of stars are the dancers. At the center of that floor is a silent conductor, Sagittarius A. Its enormous mass, equivalent to more than 4 million times that of the Sun, generates a gravitational field so powerful that it forces nearby stars to move at astonishing speeds, as if they were tied to an invisible string. Without this gravitational core, the bustling galactic center would be chaotic, and many stars could even escape the galaxy, getting lost in intergalactic space. But the influence of Sagittarius A does not end at the central bulge. Although its direct attraction decreases with distance, its presence stabilizes the galactic core and contributes to the overall order of the Milky Way. It acts as an anchor that maintains the structure of the bulge and regulates the rotation of stars and gas in the surroundings. Without a supermassive black hole at the center, the evolution of the galaxy would have been very different. Star clusters could disperse more easily, and the formation of new stars would be less efficient due to the lack of a dominant center of gravity. Does Sagittarius A influence the famous spiral arms? Indirectly, yes. The spiral arms are like waves that travel across the galactic disk, and the balance of the entire structure depends on the total mass of the core, including that of Sagittarius A base. Furthermore, its presence affects the distribution of gas and dust, facilitating or hindering episodes of star formation in areas near the center. If the black hole were to suddenly increase in mass, it could even alter the shape and rhythm of the entire galaxy, triggering extreme phenomena such as the collapse of clusters or the expulsion of stars. Ultimately, Sagittarius A is much more than just a simple matter-devouring monster. It is the invisible axis around which the complex machinery of the Milky Way revolves. Without it, the history and future of our galaxy would be radically different. Who would imagine that the greatest architect of the Milky Way is, precisely, its darkest and most mysterious heart? Why do some black holes launch powerful jets of matter at speeds close to the speed of light, while others, like Sagittarius A, seem to remain silent? This mystery has fascinated astrophysicists for decades. Relativistic jets are one of the most spectacular phenomena in the cosmos, true cannons of particles and radiation that stretch across thousands of light years, escaping the gravitational clutches of these cosmic monsters. But Sagittarius A, the black hole at the heart of our galaxy, does not generate these impressive jets. What accounts for this marked difference? To understand it, it's necessary to explore what conditions allow for the emergence of these jets. In active black holes, like those found in the cores of distant galaxies, matter falls toward the event horizon, forming an extremely hot and turbulent accretion disk. This material, as it spins and heats up, generates intense magnetic fields that channel some of the energy and matter toward the poles of the black hole, launching them into space in the form of relativistic jets. It's as if, instead of swallowing everything, the black hole spits out part of what it tries to devour, sending it to unimaginable distances. However, Sagittarius A is a surprisingly quiet black hole. Although it has millions of times the mass of the Sun, the amount of material surrounding it that manages to fall into its interior is very low compared to other more active supermassive black holes. Without a constant and dense flow of gas and dust, the energy and pressure needed to form those powerful jets are not reached. It's like having a giant water pump, but without enough liquid to create a strong jet. The machinery is there, but the raw material is missing. Could this change in the future? If at any point a massive gas cloud or a star were to come too close to Sagittarius A, it could trigger a phase of greater activity and perhaps the formation of jets. For now, the relative calm of Sagittarius A allows us to study a supermassive black hole in a low-activity phase, contrasting with its noisier and more violent relatives in other galaxies. The absence of jets reminds us that, Although black holes share many characteristics, their environment and history can make them as different as two galaxies separated by millions of light years. The comparison between Sagittarius A and other black holes with powerful relativistic emissions remains an active field of research. What exact factors determine the presence or absence of jets? How does this influence the evolution of galaxies? These questions keep astronomers awake as they watch closely, waiting for the moment when Sagittarius A finally decides to roar. What happens when a star is born, lives, and dies right next to an invisible monster like Sagittarius A? The center of the Milky Way is such an extreme place that it challenges everything we know about stellar life. Just a few light years from the supermassive black hole, stars face conditions that would be lethal in any other region of the galaxy. Immense gravitational fields, intense radiation, and a chaotic dance of forces that can tear them apart or, incredibly, give them life. But how do some stars manage not only to survive, but also to form so close to an abyss that devours everything? The mystery begins with stellar formation. In theory, the brutal gravity of Sagittarius A should prevent gas and dust from clumping together to give rise to new stars. However, astronomers have detected young, hot stars orbiting dangerously close to the galactic center. How is this possible? One of the most intriguing hypotheses suggests that violent collisions between gas clouds, accelerated by the black hole's gravity, compress the material with such force that they trigger the birth of new stars. It's like making diamonds under unimaginable pressure, but on a cosmic scale. The life of stars in this environment is anything but tranquil. Their orbits are constantly distorted by the gravitational pull of Sagittarius A, driving them to incredible speeds. Some of these stars, known as S stars, complete an orbit around the black hole in just a few years, something unthinkable in other parts of the galaxy. This proximity puts them at constant risk. A small deviation could send them hurtling toward the event horizon, condemning them to disappear forever. Or conversely, they could be thrown at such high speeds that they escape the galaxy, becoming hypervelocity stars. But the challenges don't end there. The environment near Sagittarius A is saturated with radiation and energetic particles, which can tear apart the atmosphere of smaller stars or alter the life cycle of more massive ones. Some may lose a significant portion of their mass due to these effects, while others could merge in close encounters, generating even more exotic objects. Additionally, the possibility of supernova explosions near the black hole adds another layer of complexity, as the resulting shockwaves can disturb the delicate balance of surrounding gas and dust, influencing the formation of future stellar generations. Ultimately, the life of stars near Sagittarius A is a balance between destruction and creation. It is a natural laboratory where physics is pushed to the limit and where astrophysicists seek answers to fundamental questions about stellar evolution in extreme environments. Could the presence of a supermassive black hole be, paradoxically, both a killer and a creator of stars? In the dark heart of the Milky Way, reality surpasses any fiction. What would happen if a star managed to escape the gravitational pull of the center of the galaxy and shot out at such a high speed that it could leave the Milky Way forever? This phenomenon, although it sounds like science fiction, is real and is known as hypervelocity stars. These stars are true cosmic projectiles capable of traveling at speeds exceeding 1,000 kilometers per second, much faster than any other star in our galaxy. But how is it possible for a star, with all its mass and energy, to reach such speed? The key lies in the interaction with a supermassive black hole like Sagittarius A. When a binary star system, meaning two stars orbiting each other, gets too close to the black hole, extraordinary events can occur. If one of the stars falls into the gravitational trap of Sagittarius A, the other can be violently ejected outward. It's as if Sagittarius A acts like a gravitational slingshot, stealing one star and catapulting the other out of the galactic core. This process, known as the Hills mechanism, was proposed over 3 decades ago and today we have direct observations that confirm it. But what fate awaits these runaway stars? Once expelled, many of them traverse the galactic halo and, if their speed is sufficient, can completely escape the gravity of the Milky Way. They travel alone, far from the regions where they were born, and roam the intergalactic space for millions of years. These hypervelocity stars are often young and massive, although some older and less luminous ones have also been identified. For astronomers, each of them is a messenger carrying valuable information about the extreme environment of the galactic center and the gravitational power of Sagittarius A. The study of hypervelocity stars not only reveals the extraordinary effects of extreme gravity, but also helps us understand the dynamics and history of the Milky Way. How many of these stars have already escaped? Could some cross at some point near the solar system? Although the probability is minimal, the reality is that the universe is full of surprises, and hypervelocity stars are a reminder that at the heart of the galaxy, nature plays by rules where speed and gravity reach unsuspected limits. Why are there young stars so close to a supermassive black hole like Sagittarius A? This question has puzzled astronomers for years because, in theory, the brutal environment of the galactic center should prevent the formation and survival of newly born stars. The intense gravitational pull, extreme radiation, and continuous bombardment of particles seem like lethal conditions for any gas cloud trying to collapse and give rise to a new star. However, detailed observations have revealed the presence of young, hot, and massive stars orbiting at surprisingly close distances to the very heart of our galaxy. Is it possible that these stars formed right there, next to Sagittarius A? To understand the mystery, imagine trying to light a candle in the middle of a tornado. The galactic center is such a chaotic and violent place that traditional theories of star formation don't seem to fit. Still, astronomers have proposed several ingenious hypotheses. One suggests that gas clouds could, under exceptional circumstances, resist the gravitational tide, fragment, and form stars even in these extreme conditions. Another intriguing possibility is that the young stars formed much farther away, in calmer regions of the galaxy, and then migrated toward the center, perhaps dragged by gravitational interactions or the merging of star clusters. But how could these young stars survive such a risky journey? If a star gets too close to Sagittarius A, the black hole could easily tear it apart with its tidal force. Some models propose that compact groups of stars, known as clusters, could protect their members during the journey to the galactic center. It's like a flock of birds traveling together to shield themselves from the stronger winds. Upon reaching the neighborhood of Sagittarius A, the stars might become trapped in stable orbits, surviving the hostile environment thanks to their speed and the mutual protection of the original group. However, no explanation is completely satisfactory. The existence of young stars so close to Sagittarius A remains one of the great enigmas of astrophysics. Are we underestimating nature's ability to challenge our models? Or are there still unknown processes that allow star formation in the most unlikely places in the universe? Solving this mystery would not only help us better understand the center of the Milky Way, but also decipher how black holes work and their influence on galactic evolution. For now, the young stars of Sagittarius A remind us that the cosmos always holds surprises, even in its darkest and most extreme corners. Is it possible that a black hole can help us understand the deeper laws of the universe? Sagittarius A is, in fact, one of the most extreme natural laboratories to test general relativity, the revolutionary theory proposed by Albert Einstein over a century ago. General relativity tells us that gravity is not an invisible force acting at a distance, but a curvature in the very fabric of space-time. But how do we verify this in reality? The center of our galaxy, with its monstrous black hole, offers the perfect opportunity to do so. The stars that orbit close to Sagittarius A behave like true space probes. What happens when a star speeds by the black hole? This is where relativistic effects come into play. The trajectory of the stars is not a simple ellipse, but experiences precession, meaning the orbit gradually rotates. like the pendulum of a clock that never follows exactly the same path. This phenomenon, predicted by general relativity and observed in detail in the S-stars, is direct evidence that space and time truly distort near such a massive object. Light also does not escape the influence of Sagittarius A. When light rays pass close to the black hole, their path curves due to the intense gravity, an effect known as gravitational lensing. Can you imagine seeing a star in a different position than its actual location, just because its light has been bent by the black hole? That is exactly what happens near Sagittarius A. Even time itself behaves strangely. The closer something is to the event horizon, the slower time passes for that object compared to a distant observer. This is the so-called time dilation, a startling prediction of general relativity that Sagittarius A allows us to observe and measure. Scientists have used the precision of the most advanced telescopes to track the movement of stars around Sagittarius A for years. Every small deviation, every change in speed or direction is compared with the mathematical models of general relativity. So far, observations fit perfectly with Einstein's predictions, confirming that his theory remains valid even in the most extreme environments we can study. However, astronomers continue to search for deviations because any tiny difference could reveal new phenomena or even open the door to physics beyond relativity. Thus, Sagittarius A becomes a cosmic stage where theory and reality meet. Thanks to the study of this black hole, we continue to test the limits of human knowledge about time, space, and gravity. Will there be anything that escapes general relativity? For now, Sagittarius A keeps its secrets closely guarded, but each observation brings us a little closer to understanding how the universe truly works. What happens to time and light when they approach a gravitational monster like Sagittarius A? To understand this, we must first remember that gravity not only attracts objects, but also deforms the very fabric of space-time. This distortion is so strong near a supermassive black hole that everyday rules cease to function. Time, in the presence of extreme gravity, does not pass the same for everyone. The closer you are to the event horizon of Sagittarius A, the slower time passes compared to a distant observer. It's as if every second next to the black hole stretches and becomes endless, while for someone thousands of light years away, that same second would barely be perceptible. Have you ever wondered if it would be possible to see the future by traveling close to Sagittarius A? In a way, yes. If a spaceship could get close enough and then move away, its occupants would find that while only a few hours passed for them, years, decades, or even centuries would have elapsed on Earth. This phenomenon, known as gravitational time dilation, was predicted by Einstein's theory of relativity and is confirmed in places like the galactic center. Time, therefore, is not a universal constant. It is malleable, stretching and compressing according to the intensity of the gravitational field. Now, what happens to light? Light attempting to escape from the vicinity of Sagittarius A experiences an effect called gravitational redshift. This means that its frequency decreases, its waves stretch, and the energy it carries reduces. If a star, for example, were too close to the black hole, its light would reach us tinged red, as if it were losing strength while trying to flee from the gravitational pull. This effect allows us to indirectly measure the strength of the gravitational field around Sagittarius A and provides clues about what happens beyond what we can directly observe. The gravity of Sagittarius A Tau also plays with the trajectory of light. Around it, space is so curved that light rays can bend and even orbit the black hole before escaping or succumbing to their final fate. This phenomenon, known as gravitational lensing, can create multiple distorted images or even rings of light, called Einstein rings. Thus, not only is time distorted near Sagittarius A, but also the very perception of reality, challenging our intuition about how the universe works and reminding us that, at the heart of the Milky Way, the laws of physics reach their most extraordinary limits. What does destiny hold for the dark heart of our galaxy? Sagittarius A seems immutable and eternal, but the reality is that, like everything in the universe, it also has a story with a beginning and an end. Although its timescale challenges our imagination, astronomers have made fascinating predictions about its future. Will it continue to absorb matter endlessly, or will its environment change radically over the eons? In the coming millions of years, Sagittarius A will continue its relatively quiet life, occasionally devouring clouds of gas, dust, and perhaps some unfortunate star that ventures too close. However, the amount of material available in the galactic center is not infinite. As Sagittarius A consumes or expels its food supply, its activity may decrease even further, becoming increasingly silent and difficult to detect, like a fire that goes out when there is no wood left. But does that mean its influence will end? Quite the opposite. Its gravity will continue to dominate the center of the Milky Way, guiding the movement of stars and gas around it. The future of Sagittarius A could also be marked by cosmic encounters of epic proportions. What would happen if, at some distant point, another galaxy collided with ours? In that scenario, it is likely that the supermassive black holes of both galaxies would end up drawing closer, orbiting each other in an increasingly tight dance, until merging in a colossal explosion of gravitational energy. This process would release gravitational waves so powerful that they would propagate through the universe, leaving traces that observatories could detect even millions of years later. At even more extreme timescales, when the Milky Way has exhausted much of its gas and the formation of new stars has ceased, Sagittarius A could become one of the last remnants of activity in the galactic core. If the universe continues to expand and cool, there will come a time when black holes are practically the only remaining objects. Sagittarius A, like all black holes, would lose energy through Hawking radiation, an incredibly slow process. Could it eventually disappear, evaporating completely? According to current physics, yes, but that fate is so far in the future that it is almost inconceivable. We are talking about a period much greater than the current age of the universe. Thus, the future of Sagittarius A is written in the longest pages of the cosmos, a silent guardian that sooner or later will witness the transformation, aging, and eventual fate of the center of our galaxy. Its story, still far from its conclusion, reminds us that even the most powerful giants of the universe are subject to the inexorable passage of cosmic time. What would happen if two supermassive black holes, like Sagittarius A, faced each other at the center of the galaxy? Although the idea seems straight out of science fiction, black hole mergers are real events that have been detected in the universe, although they generally involve much smaller black holes. But is it possible that our central black hole could someday collide with another of its kind? Supermassive black hole mergers typically occur when two entire galaxies collide, and over time, their cores draw closer together. In this scenario, each galaxy brings its own black hole, which begins a gravitational dance, orbiting around each other and losing energy through the emission of gravitational waves. Over millions of years, this cosmic pair eventually merges into one, releasing a colossal amount of energy in the form of gravitational waves. This process is so violent that for a moment, space-time itself shudders in the depths of the universe. Could Sagittarius A experience such a merger? The Milky Way is not an isolated galaxy. It is surrounded by satellite galaxies and, in the distant future, will have an inevitable encounter with Andromeda. When both galaxies merge, their cores will do so as well, and it is likely that the central black holes will spiral towards each other, repeating the cycle that nature has followed countless times. This collision will not occur within a human lifetime, but rather in several billion years, yet the consequences will be profound. The resulting merger will create an even more massive black hole, capable of influencing the fate of the new galaxy. But what do these encounters mean for the universe? Besides being natural laboratories to study extreme physics, Supermassive black hole mergers are responsible for the most powerful gravitational waves we can detect. These waves propagate through the cosmos, and while they barely alter our surroundings, they contain invaluable information about the nature of gravity, the structure of space-time, and the growth of galaxies. Each merger is like a unique signature in the history of the universe, an echo of cataclysms that occurred at incomprehensible distances. Ultimately, Sagittarius A is destined to witness and be a protagonist in one of the most spectacular phenomena of the cosmos, the union of invisible titans that reshape entire galaxies. Although these mergers are incredibly rare and slow from our perspective, their impact transcends human scales and reminds us of how dynamic and astonishing the universe we live in truly is. When we think of a supermassive black hole like Sagittarius A, it's natural to wonder, can it influence life here on Earth in any way? At first glance, it might seem that, being over 26,000 light-years away, its presence is completely alien to our daily lives. However, the reality is that Sagittarius A has an indirect but fundamental impact on the environment where life as we know it emerged. Its immense gravity plays an essential role in the balance and structure of the Milky Way, maintaining the galactic bulge and the orbits of millions of stars. If the galactic center were radically different, the evolutionary history of the galaxy, and thus of the solar system, could have been entirely different. Now, is there any real danger that Sagittarius A could directly affect Earth? The immediate answer is no. The distance is so vast that even the powerful gravitational effects of the black hole have no direct influence on our planet. It's like living on the outskirts of a city while the heart of that city is an active volcano. As long as we stay in our neighborhood, the volcano is irrelevant to daily life. In fact, the gravity of Sagittarius A is imperceptible in our local environment, overshadowed by that of the Sun and nearby planets. However, the existence of Sagittarius A could have indirectly shaped the fate of life on Earth. For example, the active phases of supermassive black holes can emit formidable amounts of energy and radiation in the form of relativistic jets and galactic winds. What would happen if Sagittarius A became much more active? In that case, the radiation could alter the chemistry of interstellar gas clouds, affect star formation, and even modify the amount of cosmic rays reaching the solar system. Fortunately, Sagittarius A is currently a rather quiet black hole, allowing life to develop without major disruptions from the galactic center. Is there any connection between Sagittarius A and the so-called mass extinction events on Earth? Although there are speculative theories suggesting that bursts of intense radiation from the galactic core could have planet-wide consequences, there is no solid evidence directly linking these phenomena to extinction episodes in Earth's history. In fact, most of the dangerous radiation is absorbed or deflected by the galaxy's magnetic field and by Earth's atmosphere, acting as a natural shield. Thus, the black hole at the galactic center remains a background player, powerful yet distant, whose role in the life of our planet is primarily that of a silent architect of the cosmic structure we inhabit. In summary, Sagittarius A does not pose a direct threat to our existence. Its influence manifests on the grand stage of the galaxy, shaping the environment where life could arise, but its distance and relatively calm state have allowed us to evolve in relative peace. If its activity were ever to increase dramatically, the effects could be felt even here, but the odds of this happening on a human timescale are practically nil. Ultimately, the presence of Sagittarius A is a reminder that we are part of a dynamic galaxy, where invisible giants play fundamental roles in the history of everything we know. When talking about Sagittarius A and black holes in general, myths and misconceptions abound that can distort our understanding of reality. Does Sagittarius A really act like a cosmic vacuum cleaner that devours everything that comes near it? This is a fairly common belief, but the reality is much more subtle. Although its gravity is colossal, it only affects objects that come too close to its event horizon in an extreme way. The rest of the galaxy, including our solar system, orbits peacefully at a safe distance. In fact, if the Sun were replaced by a black hole of the same mass, the Earth would continue to orbit just the same, only in complete darkness. Another frequent mistake is thinking that Sagittarius A is like an intergalactic portal or a doorway to other universes, as suggested by some science fiction stories. However, current physics does not support the existence of space-time tunnels connected to supermassive black holes. As far as we know, nothing can escape from its interior, not even the information that falls into it, which has led to philosophical and scientific debates about the fate of that information, but not to cosmic travel between galaxies. Is it true that black holes are completely invisible? Not exactly. Although Sagittarius A does not emit its own light, what really gives it away is the material surrounding it. The gas and dust falling towards it heat up to extreme temperatures and emit radiation in different wavelengths, especially in radio and X-rays. This is how scientists manage to detect it and, over time, even obtain an image of its shadow. In other words, it is invisible only in the traditional sense, but it leaves clear traces in its environment. There is also the misconception that black holes, including Sagittarius A, grow uncontrollably and will eventually swallow the entire galaxy. This is far from the truth. The rate at which Sagittarius A accumulates mass is surprisingly low. In fact, it is a quiet black hole compared to the cores of active galaxies, where black holes devour matter at frantic rates and release enormous amounts of energy. Our central black hole consumes so little material that on human scales, it is practically harmless to the surrounding galaxy. Finally, many people believe that the study of Sagittarius A's and black holes is a purely theoretical topic, reserved for mathematicians and physicists in isolated laboratories. But the reality is that its research has had a profound impact on our technology and on how we understand the universe. From the verification of general relativity to the development of precision telescopes, the study of these extreme objects has allowed us to advance in everyday areas such as GPS navigation or satellite communications. Thus, Sagittarius A is not just a distant enigma, but a key to understanding the cosmos and our own existence. Despite the enormous advances in understanding the galactic center, Sagittarius A remains one of the greatest enigmas of the cosmos. What really happens in the vicinity of the event horizon? Although theory predicts that matter and energy cannot escape, physicists still debate whether the information that enters is lost forever or, in some way, survives in forms we do not fully understand. This question, known as the information paradox, challenges our deepest understanding of quantum physics and general relativity. Solving this mystery would be like finding the key piece of a puzzle that could revolutionize our view of the very nature of the universe. Another fascinating question revolves around the formation of Sagittarius A. How did a black hole millions of times the mass of the Sun come to occupy the heart of the Milky Way? Was it the result of the merger of smaller black holes, or did it form from the collapse of a primordial gas cloud in the dawn of the galaxy? Answering this would allow us to decipher not only the history of our galaxy, but also that of many others in the universe. Furthermore, scientists wonder why Sagittarius A is relatively quiet compared to other supermassive black holes that emit powerful jets of energy. Is it temporarily asleep, or is there something in its environment keeping it calm? The environment of Sagittarius A poses even more questions. For example, the presence of young stars near such a massive black hole challenges traditional ideas about star formation. The intense gravitational forces and radiation seem incompatible with the emergence of new stars, and yet there they are, orbiting at dizzying speeds. How did they manage to form in such a hostile environment? Or were they transported from another galactic region by unknown mechanisms? Solving this paradox could reveal astrophysical processes never before imagined. Finally, the role of Sagittarius A in the future evolution of the Milky Way is another open question. Could it, at some point, awaken and trigger an active phase capable of altering the structure of the galaxy? Are there dark matter objects accumulating in its vicinity, influencing its behavior or even its growth? And beyond all this, what secrets do the movements and interactions of matter and energy hold so close to the limits of known physics? Each of these questions keeps the scientific community on edge, and their answers could completely transform what we believe we know about the universe and its fundamental rules. What makes a black hole like Sagittarius A one of the most fascinating objects in the universe? Why, despite its invisibility, has it become the epicenter of so many mysteries and scientific discoveries? Sagittarius A is much more than just a supermassive black hole. It is the dark and pulsating heart of our galaxy, an enigma whose existence challenges our understanding of space, time, and matter. Imagine a place where the known laws of physics bend and, in some cases, seem to break. A site where gravity is so intense that not even light can escape. There, at the center of the Milky Way, this silent colossus hides, marking the rhythm of the cosmic dance of stars, gas, and dust around it. Can an invisible object be so important in the evolution of an entire galaxy? The answer is yes. Sagittarius A not only shapes the movement of millions of stars, but could have been crucial in the formation and development of the Milky Way as we know it. Its gravitational influence is like a conductor's baton, orchestrating the movement of celestial bodies, and its history is intertwined with our own existence. Analyzing Sagittarius A is like looking at the inner workings of a galactic clock, where each gear depends on the invisible force of its core. How far can our knowledge about Sagittarius A go? Every time astronomers manage to capture new data, more questions arise. What really happens beyond the event horizon? Is the information that falls there lost forever, or is there any way to recover it? These questions are not mere curiosities. They push the limits of the most fundamental theories of physics, from general relativity to quantum mechanics. Sagittarius A thus becomes a natural laboratory to explore the boundaries of human knowledge, a constant reminder of how much we have yet to discover. The future of research on Sagittarius A promises new findings and challenges. Technological advances, such as even more powerful telescopes and space observatories, will open windows to phenomena that we can barely sense today. Could Sagittarius A one day merge with another black hole? How will it affect the galaxy in the coming millions of years? Ultimately, studying this dark heart is not just a matter of science, but also an invitation to humility and wonder. It reminds us that, even in the center of the most absolute darkness, there are secrets waiting to be illuminated by human curiosity.